Creation of surface waves. Surface waves are created by wind, as friction creates surface on the top of the water. This affects the water molecules, causing them to oscillate. Wind waves have a certain amount of randomness, and wind waves differ in height, duration, shape, with limited predictability. As the wind creates friction on the surface of the water, it causes the particles to oscillate in a circular motion. This is then transferred down the water column, creating more oscillation as the particles move in circular motions. Surface waves can travel around the world at great distances. Propagation of waves. This is a way that any wave travels. Waves in the ocean can travel thousands of miles before reaching land. Wind waves on Earth can range from small ripples to waves over 100 foot high. The great majority of large breakers as seen at a beach result in distant winds. 5 factors influence the formation of flow structures in wind waves. The first being wind speed. The second is the undisputed distance of water over which wind blows without significant change in direction. This is also known as fetch. 3 is the width of an area affected by fetch. 4 is wind duration, and 5 water depth. The mathematics of waves. Wind waves propagate along the surface of the water in the air. As particles oscillate in circular motions, this decreases through the water column. For pure periodic waves, the motion of small wave amplitude wave well approximates by the photos shown below. On the other hand, the very short wavelength of surface tension plays an important role, and the phase speed of these gravity pillar waves can be in deep water approximated by the other diagram shown below. The wavelength is very long compared to the water depth and phase speed. By taking the limit of c when the wavelength approaches infinity can be approximated by the graph shown below. The end of a surface wave. As a surface wave reaches shallow water, the wave that is oscillating all the way down through the water column is forced upwards. This increases as the water comes into shore. As the wave height increases, it pushes up out of the water, which means that the wave is pushed up until the wave reaches a point at which it breaks. Waves can also refract off objects and be reflected from coves. Theories of tidal propagation. The first being equilibrium theory, and the second being dynamic theory. The first theory is equilibrium theory. This theory assumes that there are no land masses in the sea, and that the seafloor is undefined as a deep ocean. This means that the ocean is the same depth all the way around, and that the seabed is flat. This theory takes into account the gravity of the sun and moon. However, the moon's gravitational force is 2 times the amount of the sun's due to its distance from Earth. If you imagine the sun and the moon on either side of the world, and the ocean is uniformed all the way around, the water is pulled from one point to another, so there are 2 high points and 2 low points. This is what creates the 6-hour tides. Neap tides are weaker tides, however, and this is caused by the sun and moon being at 90 degrees from each other. This causes a contrast in gravitational forces that interfere with the oceans, creating more balance and less tidal movement. The second type of tide is a spring tide. These are strong tides, and these are caused by the sun and the moon being aligned with equal pulling force from both sides. This creates 2 larger bulges and 2 small bulges on the Earth's oceans, creating large tide differences. The second main theory is the dynamic theory. This is a little bit more complicated, and this theory takes into account land masses. However, if the equilibrium theory was correct, it would mean that the same tides apply in the Mediterranean as in the other seas, which we know isn't true. This dynamic theory takes into account centrifugal force. Centrifugal force is due to the Earth's rotation and causes an outward force from the Earth's core. However, the Moon orbits the Earth, and the Moon has its own gravitational pull. When you take into the account of this, it puts the balance of the Earth's centrifugal force not directly in the middle, but actually a little bit out to the side. This creates a spinning motion of the Earth on its own axis, creating an outward force of centrifugal force. This rotation in a small circle that the Earth has creates a swelling motion. If you imagine a bucket of water being swelled round, this is how the tides work on Earth. Taking this into account and the gravitational pull of the Moon and the Sun, and the force of the world being swelled round, this creates the tides. Due to the Mediterranean not being large enough to be greatly affected by the tides, it is reliant on the Strait of Gibraltar. Due to the small opening, there is not enough space to create large tides for the water to flow in and out into the Pacific. Now, as water flows around the Earth following the Moon, it's stopped by land masses as well. This means that reflection is involved from the coast, which creates a rippling across the sea, and this is how high and low tides are created. As the wave is reflected, it loses energy. However, 6 hours later, the second gravitational pull arrives, creating the 6-hour tide cycle. The second part of dynamic theory involves the Coriolis effect. This effect is caused from the Earth's rotation. In the northern hemisphere, it occurs to the right of the equator, and from the southern to the left. Anthrodromic points are points of where the tide stays the same. So if you imagine the centre of the Earth and a point being in the middle, you'd imagine that the tide does not change. There are 5 of these in the Pacific and 3 in the North Sea. So how is that so? This is defined by the wave speed limit. If waves exceed the speed of the wave limit, the waves are broken up into smaller waves, and this creates more anthrodromic points around the world. The way you can calculate this is via the Earth's gravity times ocean depth equals the speed limit squared. So roughly the speed limit works out to be 435 miles per hour. However, at the equator, waves need to travel at 994 miles per hour due to the Earth's spin, and this exceeds the speed limit. This leads to more breakups. This means that you can have many orthodromic points around the world. The further away from an orthodromic point, the higher the tide points. So if you imagine a bucket, each anthrodromic point is the centre, and the tide spins around that point. Movement of surface currents. The Ekman spiral is a term used to describe water being moved by wind on the surface of the ocean. As the wind creates movement on the water via friction, the water molecules oscillate in a circular motion. This creates movement further down the water column, as the water is oscillating more and more as it gets down in smaller and smaller amounts. As wind affects the water, it's worked out that roughly 1 in 100th of its energy is used to push water in forward motion. This water is moved at 45 degrees right of the wind direction in the northern hemisphere and 45 degrees left in the southern. This is due to the Coriolis effect, which we have previously talked about. The effects of this continues turning as the water gets deeper until it's eventually 180 degrees from the wind direction. This water piles into domes in the centre of the sea and at the left and right of the equator due to trade winds and westerly winds. The land masses trap these water currents around, which are known as basins. These wind-driven currents rotate in a clockwise motion in the northern hemisphere and an anti-clockwise location in the southern. These are also known as gyres. These gyres are vital for plankton movement, however plankton can move against the gyre. There are 5 in total. These gyres are often egg-shaped, being trapped by land masses, which means that the narrower passing between the land and the middle of the gyre means faster water currents, which often result in western boundaries being pushed closer together, causing stronger currents. Here is a map that shows all the surface-driven currents. Density-driven currents. Warm water and cold water have different densities, so where cold water is far more dense than warm water, it sinks, where warm water rises. At the poles, there is a lot of cold, icy, salty water. This water is pushed down along the seafloor, and it is pushed along to the equator, where it's then warmed up and rises again. This is called thermohalide circulation. These currents come from a global conveyor belt, which is the longest sea current in the world. These carry many vital nutrients for ecosystems in the world. Cold water contains many nutrients from the poles, which are then pushed along to upwelling points, which is where cold water is pushed up to the surface via its warming, and is then abundant on the surface for plankton to grow and thrive. This creates a vast ecosystem for many animals and is vital for the ocean's ecosystem. Recent studies have shown that as the sea level temperature rises, it is also causing it to slow down. Effects of global warming on the ocean systems. Global warming is a massive topic in today's news, and it involves the warming of the ocean's atmosphere, which is causing an increase in the ocean's temperatures. The global conveyor belt is responsible for many of the nutrient-rich waters being taken to the equatorial systems. Nutrient-rich waters are very important for species such as cobiopods and zooplankton and phytoplankton. Zooplankton is one of the main food sources for larger animals such as basking sharks, whale sharks, and many whale species. Phytoplankton can produce up to 70% of the world's oxygen supplies. Without nutrient-rich waters being put from the polar to the equatorial zones, it would mean a decrease in these species, which would create not only less oxygen in the oceans, but also a breakdown in the ocean's ecosystems. The global conveyor belt does not only have impact on species, but it also has impact on weather systems as well. For example, the Gulf Stream has a large effect on the UK's weather systems. The increase in global temperature has also increased the amount of tropical storms that are occurring, with last year having the most tropical storms ever recorded in the same time. This means that there will be more catastrophic storms like Hurricane Katrina that could devastate the world's population. Not only could we be destroying our own ecosystem and unstabilizing the planet, but we're also killing all life on the Earth. This is the effect of global warming, and the ocean systems are the primary source for all life in the world. Not much is known about the world's global systems and the ocean systems beneath us. However, many studies are ongoing into the research of how these systems work.